Hi everybody, welcome to another video in my series on computer systems. This is the second and final video for Module 4 on dynamic memory allocation. Again, if you're following along in the textbook Computer Systems, A Programmer's Perspective, this covers Chapter 9, Section 9. Now, let's remember that in our last video, video 1 in Module 4, we covered some of the basics of dynamic memory allocation, and we talked about using an implicit free list to keep track of free blocks. So if you haven't watched that video yet, go on back and check that one out. And in this video, we'll finish up by talking about explicit free lists and segregated free lists. So let's recall from part 1 of Module 4 that with an implicit free list, we use our boundary tags and we kind of just hop, skip, and jump our way along, and we go through and we actually take a look at all of the allocated blocks and all of the free blocks when we're looking for a free block to allocate, for example, with a call to malloc. Now, in an explicit free list, we're only going to maintain a list of the free blocks. We're not going to have to, again, examine every single block, right? We can kind of skip the allocated blocks because when we call malloc, we get a pointer, right? We know where those are. So there's no need to waste a bunch of time looking at those when I'm trying to search for a free block for my next allocation call. So in explicit free lists, we're just going to cut out those allocated blocks. We're only going to keep track of the free blocks. Now, the next free block could be anywhere, right? If we're not going to look at each block in turn, we have to have some way to go from free block to free block, and just having those boundary tags, just having a size and allocation flag isn't going to do that for us. So we've got to store some stuff in those free blocks that we didn't have to store in implicit free lists. Specifically, we're going to store pointers both to the next free block and to the previous free block. So every single free block that we have, we're also going to just slap a couple pointers in there right after the header tag to indicate where the next free block is and where the previous free block is. Now, we can't get rid of those boundary tags because we still need those for coalescing, right? Once we free a block, we'll add those pointers in, and that's great. But we still need to have those boundary tags so we can check the previous block, whether it's allocated or not, and the next block, whether it's allocated or not, to make sure that we can coalesce properly. So that can be a little confusing. When we talk about coalescing, I'm talking about the block that's next in the address space, or the block that's previous in the address space. The next free block will be pointed to by that next pointer inside the free block, and the previous free block will be pointed to by that previous pointer within the free block. So we have to be careful about what we're talking about when we talk about next and previous blocks, because when we deal with explicit free lists, again, the next free block could be anywhere in memory. The previous free block could be anywhere in memory. When we're coalescing, we're talking about the last block, the previous block in the address space, right? So we're talking about the block that's, you could almost think of it as physically closest to the block we just freed, and the block that's physically closest, further on down the address space in the block that we just freed. So since we only track those free blocks, like I said, we can use that payload area that normally in a free block would just be blank. We can stick our pointers in there and not use any extra space. So just to take a look at that a little bit graphically and make sure we understand what we're talking about, when we have explicit free lists, if we've got free blocks, block A, block B, block C, and these are all free blocks because, again, with explicit free lists, we don't keep track of the allocated blocks, right? We already have pointers to those. So logically, block A could have a next pointer that you see here is the green arrow that points to B. B has a next pointer that points to C. C has a next pointer that points to whatever the next free block is. And then each of those would also have a previous pointer that points back to the previous free block. So C's previous pointer in red here would point back to B. B's previous pointer would point back to A. A's previous pointer would point back to whatever's before A. So logically, it's very, very clear. It's very simple. We just have this string of free blocks with pointers to each other so we can go forward and backwards. Now, physically, though, these blocks can be in any order. So if we lay out our address space here, right, from the lower addresses over at the left to higher addresses over at the right, we could start right out with the free block A. That makes sense. That just maps to our logical map. But the next pointer for A, the green arrow, could point way, way far away to B. All right, and B can be anywhere out there in memory. So it can be way, way, way higher in memory. The previous block for pointer for B would point all the way back to A, of course, but the next pointer for B could actually go backwards in memory to C, which is actually physically living between A and B somewhere. But we don't have to worry about that. As long as we just follow these pointers to get to our next and previous blocks, everything works out great. And as far as we're concerned, we can just think of that logical map from A to B to C, whereas they can really be anywhere in memory that they end up being. So what happens when I've got myself an explicit free list and I need to allocate? All right, and that's the whole point of this, is I'm trying to allocate memory dynamically. So let's take a look at just the concept of what we would need to do to make this happen. So let's say we've got a few free blocks here up at the top. We've got a couple short free block right at the top. We have our next pointer that points down to a next much longer free block. The next pointer from that points down to another, say, shorter free block. And we've got our previous pointers pointing ourselves backwards so that we can traverse this thing in either direction. So simple enough. Now, let's assume we call malloc. Now we're going to have to allocate some stuff. And let's actually take a look at what this would look like with splitting. All right, remember splitting from our last video, where we're just going to take a free block that's actually too big for what we're trying to allocate, and we'll just split it into two free blocks so that we don't have to waste a bunch of space. All we have to do, actually, is we'll split that second free block, because that's the one that will actually fit what we need to allocate, and we just need to change our pointers around a little bit. All right, all we have to do is the actual pointers that were in the larger second free block in the middle here, those can actually just move over, right? Those are going to point to the same places. The next one is still going to point to that next free block. The previous pointer will still point back to the previous free block. Those are pointing to the same locations that they were before, so we can just copy those over, move those over into our newly split off free block. What we'll have to change, though, is the next pointer from this top block will have to change, because it was pointing at the beginning of this entire block that we've split off. It was actually pointing at the address that we're returning to malloc. It was pointing at what is now an allocated block. So we just have to change it so it points to the address of the newly split off free block. Just the same way, in that next free block in the list, we've got to change the previous pointer, right? Because it was pointing back to the now allocated block. We've just got to change that to point back to our split off free block. So this can look a little confusing, but when we think about it, all we've got to do is just maintain our pointers a little bit. If we get rid of a block, if we allocate an entire block, we just change our pointers to reflect that. If we allocate part of a block and we split, we just change our pointers to reflect that. So it's a pretty simple process, and it's not very expensive to just write these pointers into those blocks. So now that we have an idea of what it looks like to allocate when we're using an explicit free list, well, what happens when we need to free a block? Right? We have an allocated block and we're going to free it. How do we insert that newly freed block back into our explicit list? Well, we've got these things called insertion policies, which basically just addresses where in the free list do you put a newly freed block. And there's a couple that we want to be aware of. We've got last in, first out, or LIFO policy. And that just means we're going to insert the freed block right at the beginning of the free list. Right? It's very, very simple. We do that in constant time because we're always just going to take any block that we free and stick it right in the front. The problem with that is that some studies do suggest that fragmentation ends up being worse than if we do it in an address-ordered way. So what's an address-ordered way? Well, that's our address-ordered policy. In an address ordered policy, we insert the freed blocks so that the free list blocks are always in address order. So basically, we're going to make sure that actually in the physical addresses, they kind of match that logical look that we saw on the last slide. They're always going to be, the next one will always be the next highest address. The previous will be the, next lower address, so that they're always in order. The con for that is that requires a search, right? We've actually got to we've got to go through our list to find out where we need to insert this thing. But we do have studies that suggest that the fragmentation is lower. So, well, we have to, as with everything, we have to make a decision about a little bit of a trade-off. We decide, do we want to spend more time to get better fragmentation, to get better usage of the space, or do we want to save that time, do a constant time insert in a LIFO policy, but maybe not get as good of a heap usage as we could? So now that we have the basics down, let's take a look at what this looks like with all of our different coalescing cases. So the first one is where we're going to free a block that's surrounded by other allocated blocks, and that makes things pretty easy, right? That's a simple thing to start with. So the first thing we have here, notice that we have this thing called root over here. Now that's just a pointer that points to the first free block in the list. So in this top graphic here, we have the root pointer, which points to our first free block. That free block, of course, has its next pointer pointing to the next free block out wherever it happens to be. And notice that we have this little red circle here. That just indicates there is no previous pointer in our first free block, right? That could just be a null pointer or something because there's no free block before it, right? It's not going to point back to the root. It's just not going to go anywhere. We don't have a free block previous to this one. So when we free this block, wherever it happens to be, in a LIFO policy, we're going to insert it at the beginning of the list. So that just means we change the root pointer to point to this freshly freed block. We put the next pointer of the block we just freed pointing to what used to be the first free block, right? And then we update that null pointer, that kind of blank previous pointer in what used to be the first free block, to point back to our newly freed block. And of course, because it's the first free block now, this newly freed block that we just freed will have, again, probably a null pointer for the previous pointer because there's nothing to point back to. So this one is pretty simple. And you know what you're going to find? These graphics are going to look more and more complicated as we go because we're going to be doing coalescing in different cases. But the overall concept is always this simple. We just update our pointers and move on from there. So what do we do in case 2, where I have the previous block is free after I free the block in question? And remember, when we're talking coalescing, we're talking about the previous block physically, like the one that's closest in the address space. So what we'll do here is we'll just coalesce that block, and that whole coalesced block is now my newly freed block. So I insert that right at the beginning of the list. Update my root pointer to point to that newly freed and coalesced block. That one isn't going to have an actual previous pointer, remember. Change my next pointer in that new block to go to the what used to be the first block. Update the previous pointer in what used to be the first block to point back to that newly freed block that we just inserted. But the interesting thing here is, what do we do about the blocks that were the next and previous blocks of that free block that we just coalesced with? Well, that's pretty easy too. We just change up those next and previous pointers to kind of splice the newly freed and coalesced block out of the equation. So we used to have the next pointer for this one up here pointing at the free block that we just coalesced. Let's just have that point all the way to what was the next block. So you can almost think about it as moving the old next pointer from that block we just coalesced up into that previous free block. And we do the same thing with the previous pointer in the next block down. We just have that point all the way back to what was the previous block for the newly coalesced free block. So we're just going to yank that whole thing out, update the next and previous pointers on the next and previous free blocks, and then change our root pointers to put this thing at the front of the list. So again, it looks a little more complicated, but it really is pretty simple when you get down to what you're actually doing. Now, for case 3 and actually case 4 on the next slide, we're pretty much doing the same thing, right? We coalesce, we update our root pointer to point to the newly freed and coalesced block. We splice that out so that what used to be the previous and next blocks are pointing to each other. And we just, put the new pointers into that newly freed block to point to what used to be the first block with the next pointer and have a null pointer or something for the previous pointer. So I'm going to actually let you trace this out. Pause this. Take a look at how these pointers get changed, because it's the same thing as we just did in the last slide. And as we go into this next case, case 4 here, where we're freeing a block that's surrounded by other free blocks, well, we do the same thing. We're just splicing it out of 2 different chains, but we're still just going to have the root point to the newly freed and coalesced block, have the next pointer in that point to what used to be the first one. But in this case, we've actually got 2 kind of chains of free blocks where we had next and previous. We just splice it out of both of those and update those so that they're skipping it and going to the next one and previous one respectively. So once again, with this slide, take a look through it, trace these pointers, and make sure you understand how it works, but it's the same concept, right? This is great. This is computer stuff. We love thinking in algorithmic terms, and we just basically do the same approach no matter what case we're dealing with. So when we're thinking in terms of explicit free lists in comparison to implicit lists, the allocate time is linear time in the number of free blocks instead of in the number of all blocks, right? Because with implicit free list, it's linear with respect to all blocks. With explicit, it's linear with respect to just the free blocks, and that's much faster when the memory starts getting full, right? When a lot of my memory is allocated, then I'm looking at a lot fewer free blocks to find where I can allocate my next thing. It's a little more complicated to allocate and free, since we do need to splice blocks in and out of the list, and we got to keep those pointers straight, but it's not too bad. And we do need some extra space for the links, right? 2 extra words per free block. Now, does that necessarily increase internal fragmentation? Not necessarily, actually, because remember, we're going to just write over those when we actually allocate that block. So, the fragmentation things are something always to consider, but when we're dealing with it this way, it's not too bad. We're taking empty space anyway. So really, and we can always splice things out, right? So we might, in some cases, when we're doing very, very small allocations, cause a little bit of internal fragmentation, but not too bad. Now, the most common use of linked lists is in conjunction with segregated free lists. Okay, so what we can do now is we can expand on this explicit linked list idea and keep multiple linked lists of different size classes, or maybe even for different types of objects, and that gets us into our third option here, which is the segregated free list. Now, the good news is this is actually a pretty simple expansion from our explicit free list. It's basically just a bunch of different explicit free lists, and we just use each size class of blocks is going to have its own explicit free list. So we might have one list that's for blocks of of 1 or 2 words, another one that's for blocks of 3 words, another one that's for blocks of 4 words, another one that's for blocks of 5 to 8 words. We'll usually have separate classes for each smaller size, and then for larger sizes, we start expanding things a little bit so that we have one class for each 2 power kind of size. So how do we actually run this? How do we make this work? Well, we get ourselves an array of free lists, each one for some size class. And if we want to allocate a block of size n, right, whatever the size that we need to allocate is, we'll go to the appropriate free list for a size of, some m that's greater than n. All right, so because I do need my boundary tags and things. So, if I have to allocate 4, I want to go to the size list that has, size 6 in it. If we find an appropriate block in that first list we search, we'll split the block, place the fragment on its appropriate list if we need to. Right, so if the first appropriate block I find is going to leave me with 4 words left over, I can actually split that free block and put that new free block into the appropriate list that contains size 4 blocks. If we don't find a block, we'll just try the next larger class, and we'll just keep on doing that until the block is found that we can use. Now, if no block is found, that just means our heap is filled up, right? We don't have anything on the heap at all that'll do this, so we can request additional heap memory from the OS, allocate a block of n bytes from that new memory, and place the remainder as a single free block in the largest size class. So even when we have to grow our heap, we have a very simple way of grabbing the allocation that we need and then just syncing the rest of how much it grew right back into our segregated free list approach so that we can keep on doing this as efficiently as possible. Now, that's how we can allocate with a segregated list, but how do we free? Well, that's about as simple as it gets. We just coalesce and place it in the appropriate list, right? I mean, easy as can be. Now, the advantages of segregated list allocators is we get higher throughput. It's actually log time for power of 2 size classes. So, when we think about it, if we're going through an explicit free list and we're searching for a block that works, we might have to go through, if I have a large block, a large allocation, I might need to go through and look at a whole bunch of smaller blocks. With a segregated free list, I'm only going to start looking at the blocks that should actually fit what I need to find. We're going to get better memory utilization. A first fit search of a segregated free list actually approximates as a best fit search of the entire heap, because once again, I'm only looking at the classes that should contain the stuff that I need, right? So I don't have to go looking through a bunch of stuff. It's not going to be an exact one-to-one correlation to a best fit search, but it's going to be very, very close to that. And in the extreme case, giving each block its own size class is equivalent to best fit. So as we walk away from this video and this module, remember this is the last video of module 4, we want to be able to describe explicit free lists. We want to describe those boundary tags, describe the process of freeing memory with explicit free lists. Remember, it's a little more complicated, but not by much. If we just take our time and kind of follow those pointers, we're going to be in good shape. And let's be able to describe segregated free lists, both how they work and what some of the benefits are.